Alright, silly people, here's the situation. This question is just kind of a conceptual check um, of what happens if you happen to add a constant um, V naught to your potential energy. What happens to time dependent quantum states? So, typically, if you want to have a time dependent quantum state, um, you will have first a position dependent quantum state, so time independent, and you'll just multiply it by the exponent, so e to the minus I h t over h bar, where h is the Hamiltonian, um, where the Hamiltonian is defined as being um, it's the sum of kinetic energy and potential energy. In this case, I'm assuming a position-dependent potential energy, not a constant one. Um, so what happens when we throw on an additional constant additively, like that, V naught? Um, and so whenever you look at the new time-dependent wave function, assuming we're still using the same time-independent wave function to multiply it by, again, we're multiplying by minus I h t over h bar, where h prime is the new Hamiltonian, um, which is identical to the last Hamiltonian, except it has an additional v naught term. So you're doing exp minus I h t over h bar plus, or minus actually, just v naught t over h bar. And then you can separate that um, from the exponent by just pulling it out. So you'll have just minus I v naught t over h bar. So now this is the exact same thing that we got for the first time dependent wave function. That's psi of x into t. So we can conclude that psi prime of x into t is just equal to psi x and t times this factor of e to the minus I v naught t over h bar. Okay. How does that correspond to expectation values? I'm going to look at the expectation value of momentum first. So typically, the expectation value of momentum, you take the integral over all space, you do psi star, and then times the momentum operator times psi, integrate over position. And so the momentum operator is just minus IH bar with a gradient psi dx. And that's how we'll define it for now. If we add our v naught to the Hamiltonian, then we can write it like this, where I'm kind of shorthanding. These wave functions are time-dependent wave functions that we are putting in our integrand. And so the way that we defined our new time-dependent wave functions is as being like the same as the old ones times this new factor, where I have to take the complex conjugate of it now, so we'll have plus I v naught t over h bar here times the momentum operator, and then we'll have psi x t, and then you'll have minus I v naught t over h bar. the momentum operator, when we expand it, um, is a derivative over space, um, not of time, right? Um, which means the gradient won't affect the potential energy term. So this term will just cancel out this term. And you're left with the same thing as before. So P prime is just the same as P. Okay, why does that make sense? It makes sense because expectation values are um, more subject to classical physics laws than they are to quantum physical laws, right? If you operate on, this is like saying that momentum classically, if you add a constant to the potential, is the same as momentum otherwise. And that's true in classical physics just outright. Um, it took a little bit of doing to show it in quantum physics, but it makes sense that the correspondence would be the same. All right.